Hello students, welcome back to the class. Our class will be focusing on today the solutions theory part 5. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the same. Please note that parts of the content may have been generated using generative AI, which is experimental. So, what are the topics that we are going to cover today? So, our objective would be to study the colligative properties of solution, and then we will try to correlate this colligative property with the calculation of molar masses for the given solute. If I try to say put up the topics according to the NCERT, then first we will see the colligative property and determination of molar mass, then relative lowering of the vapor pressure, elevation of boiling point, okay, and some examples. Then we will also see the depression in freezing point, osmotic pressure, and abnormal molar mass. So this whole class will be in English language, okay. So what are colligative properties? First of all, the most important point about this property is that it is totally dependent upon the number of solute particles. So we have two components in a solution, which are solvent and solute. So our colligative properties are only dependent on the number of solute particle and not on the nature of the solute particle. Now these type of properties are called colligative property. Our term colligative is derived from a Latin word where co means together and ligar means to bind. First of all, what is the effect of adding a non-volatile solute to a solution? The result is that the vapor pressure of the solution decreases as soon as we add it. Then, due to which many properties are connected to the same vapor pressure and they also decrease or increase as a result of this addition of solute particle which are non-volatile in nature. The first colligative property is relative lowering of the vapor pressure of the solvent. Second is depression of freezing point of the solvent. Third is elevation of boiling point of the solvent. And the last one is osmotic pressure of the solution. Now, if I talk about the relative lowering of the vapor pressure, then it is seen that whenever we add a non-volatile solute to a volatile solvent, then the solution becomes less volatile. As a result, the vapor pressure of the solution decreases. So, Rawls tried to establish the relation between the lowering of vapor pressure with the concentration of the solute particle. Remember, it is not dependent upon the nature of the solute particle, it is only dependent upon the concentration because we are in concern with the number of solute particle. The concentration term which we used to define this was our mole fraction. And this mole fraction is related to vapor pressure as P1 equal to chi1 P1 naught. Okay. So this P1 is the pressure of the volatile solvent and it is equals to chi1, which is the mole fraction of the solvent multiplied by the pure solvent's vapor pressure. Now, if I try to do it for a binary solution, then we know that chi2 plus chi1 is equals to 1. Then chi2 will be equals to 1 minus chi1. We know it very well that the summation of all the mole fractions in a given solution is equals to 1. From that, we have derived this equation. Now, if you put it here, you will get delta P1 equal to chi2 P1 naught. Again, remember students that the pressure due to the solvent 1 will be the pressure of the solution as well, because our solute is non-volatile in nature. Okay. So we can write that the change in P1, so if you just put these values here, you will get it as delta P1, which is equals to P naught 1 minus P1. So this is just a calculation that we have done it from here. So P1 is equals to 1 minus, or you can write 1 minus chi2 P naught 1. Okay. So if you just multiply it within the brackets, you will get P1 equal to P naught 1 minus P naught 1 chi 1. Okay. Just bring all of this to the left hand side. What we will get? We will get P1 minus P naught 1 is equals to minus P naught 1 chi 1. If we multiply minus 1 on both sides, we will get P naught 1 minus P1 is equals to P naught 1. So this thing was chi 2. Okay, we have just substituted it from here. So that will give you chi 2. Finally, this term can be written as delta P1, which is the change in vapor pressure. And hence we are getting this final equation. So anyone has an issue with this derivation? So if you just substitute the value of chi 1 from this equation, you will finally get this thing where your delta P1 is the pressure of the pure solvent minus the pressure of the solution. Now, if a solution contains several non-volatile solutes, then the lowering of the vapor pressure will depend upon each of its mole fraction of the different solutes. So the equation can be written as delta P1 by P naught 1. So we have just cross multiply this P naught 1 on the left hand side to get this equation. Now, this expression here is called your relative lowering of the vapor pressure. Why? Because the vapor pressure of the solute has been decreased by some amount. So that is being written in the form of difference with relation to the vapor pressure of the pure solvent. So we tell it as the relative lowering of the vapor pressure. So again, I am repeating this thing. So we have started with P1 equals to chi 1 P1 naught. So for any volatile solvent, we can say it. So let me do it for you here. So P1 equal to chi 1. So this is chi, mole fraction, P1 naught. Okay. Now we know that chi 1 plus chi 2 is equals to 1. So this is for binary solution. If you put the value from here, you will get it as 1 minus chi 2 P1 naught. Okay. Further, if you just bring this thing on the left side, you will get P naught 1 is equals to minus P naught 1 chi 2. Just multiply with a negative sign on both sides. You will get P naught 1 minus P1 is equals to P naught 1 chi 2. Again, remember this chi 2 is for the solute and chi 1 is for the solvent. Similar to that, P1 is for the solvent and P naught 1 is for the pure solvent one. So this is your Raoult's law. Now we can write this P naught 1 minus P1 as delta P, and this thing will be equals to P naught 1 chi 2. Okay, so this was our equation. I hope it is clear to all of you now, whoever has missed this part. Now we got this relation here. I have just multiplied this P naught 1 on the left hand side to get this final equation. Now why it is called as relative lowering? Because our vapor pressure has been decreased by delta P amount. Okay. And if we try to find this value, in relation with this P01, then we call it as relative lowering. This is lowering and this whole term is relative lowering. Next, our equation can be written as, for mole fraction of chi2, we can write number of moles of the solute plus total number of moles. This is the formula for the, say, mole fraction. Now, moving on further, we know that the solvent's concentration is very high. So, this law is itself true for dilute solutions. Dilute means we are adding very less amount of solute. So, all of the colligative properties law are mostly applied and are only validate to dilute solutions, because there is no interaction in that case as the solute particles are far apart. But if you go on increasing the number of solute particles, they will come together and hence will result in some interaction. So we always take it for the dilute solution. If it is dilute, that means solute particles are very less as compared to the solvent particle, and hence we can neglect the N2. So N1 plus N2 can be written as N1 alone. If we do that thing, we get our final equation like this. Now, number of moles of 2 can be calculated as the given mass of 2 by the molecular mass of 2. Similarly, N1 can be calculated as, which is the number of moles of solvent, as the given mass of the solvent divided by the molar mass of the solvent. So, this is our finally required equation. Most of the time, we deal with this approximation. In many questions, you will not have this N2 value, and so don't panic in that case. Just use this equation directly. So here W1 and W2 are the masses, and M1 and M2 are the molecular masses of the solvent and solute. So our main goal is to calculate the molar mass of the solute. So this is the main goal of every colligative property, that we are interested in calculating the molecular mass of the unknown solute. So if you are doing this, or you are adding this solute to a known solvent, then you must have the idea of its molecular mass and the weight, and you can easily measure the pressure from the experimental setup, and hence you can get your molecular mass of the solute. So just listen to each and every word that I am saying, because each word is very important here to get the clear picture of the whole colligative properties. Then the vapor pressure of the liquid increases with increase of temperature. We know it. How does it increase? So whenever you are adding, you are increasing the temperature, it means you are providing thermal energy to your liquid. So if you take a liquid and start heating, it will gain thermal energy, and finally this thermal energy will overcome the intermolecular force between the molecule, and the molecule will go into the gaseous phase. So this is the process of conversion of your liquid into the gaseous state. So that thing has been mentioned here, that due to this, the vapor pressure will increase, because your vapor pressure is simply the pressure provided due to vapor. If the number of particles is increasing, then your pressure will also increase. Now, if I define boiling point of a liquid, then it is that temperature at which the vapor pressure of the liquid is equals to the atmospheric pressure. Now, let me explain this thing with the help of this diagram here. Suppose you have your liquid here. You have your liquid molecule here. The only reason your liquid molecule are not getting converted into the gas phase is that there is atmospheric pressure that is present. Okay, the atmospheric pressure around you is the only reason that your liquid is in the liquid state. Or else, if this pressure wasn't here, then this liquid would have broken the intermolecular force and went into the vapor phase. So now your vapor pressure of this, say, liquid is less as compared to this atmospheric pressure. But when you start heating this thing, okay, when you start heating this thing, then what will happen? This molecules will gain kinetic energy. Their kinetic energy will increase, and it will increase to an extent where it will apply more pressure than the atmospheric pressure. Then this pressure, and at this point your molecule starts converting into the vapor, and it is called as the boiling point. I hope you are getting this very picture of this boiling point thing. If you are clear about this, then you can clearly understand that what is the reason behind elevation in the boiling point. So the vapor pressure should be equal to the atmospheric pressure for boiling. This is the thing for boiling liquid. Now, if you add a non-volatile solid particle, then the vapor pressure will decrease. Hence, you will have to apply more temperature to keep your or to make your vapor pressure equal to the atmospheric pressure. So, if you are not understanding it, you will get the idea very clear when I will make you see the graph. Suppose, for example, if the water boils at 373.15 Kelvin, which is your 100 degrees Celsius, and this thing happens at 1 bar pressure. Okay, so this boiling point is only valid at the atmospheric pressure. If you do the same thing in a different way, okay, if you do the same thing on a different pressure, then you won't be able to do the boiling. Now, suppose we add sucrose to your water, then you will see that now your vapor pressure has been decreased. Okay, the vapor pressure of the aqueous solution of the sucrose will decrease because sucrose is non-volatile in nature. So this is your lowering in vapor pressure. As a result of this, you will see that the boiling point has increased. So is my voice clear? So as a result of decrease in the vapor pressure, you have to apply more and more temperature. And thus we have a higher boiling point as compared to the pure solvent. So I hope you are getting this thing. So once you are able to understand that there is a decrease in vapor pressure and what is boiling point, then you will be able to do this thing. Okay. So if you are facing difficulty, then don't worry. We have a Hindi version of the same lecture uploaded in a website in a few days. If it is not available, then in 1 to 2 days it will be there. So don't worry about this thing. But still, you can go on with this lecture so that you can get a idea about what is going on. And then if you go and watch the Hindi lecture, then it will be more clear. Okay, so don't worry. So if you have not understood this, then let me show the same thing with the help of a graph. And remember, this graph is very, very important. Suppose this orange line here is depicting the vapor pressure of the pure solvent. Okay. Now, this violet line is depicting the vapor pressure of the solution upon the addition of non-volatile solute. So we have seen it. Whenever you add a non-volatile solute, the vapor pressure decreases. And you can see that here we have a lower vapor pressure. There is a difference between these two at a same temperature. Okay. So at a same temperature, solution is at a lower vapor pressure. Suppose this is your vapor pressure of solution and your pure solvent is at a higher vapor pressure. So this is your vapor pressure here and here at the same temperature, right? Now, if you keep on increasing the temperature, the vapor pressure of both the solvent and solution are increasing. But to touch this boundary of 1 atm, your solution requires a greater temperature, which is TB. Okay. Whereas your pure solvent acquires this same vapor pressure at a lower temperature, which is T0B. Okay. So this is the thing that is important, that due to this initial increase in the vapor pressure, the solvent, pure solvent, reaches the 1 atmospheric pressure easily as compared to the solution thing. And as a result, it starts boiling easily, because boiling starts only when your vapor pressure of the solution becomes equal to the atmospheric pressure or 1 atm. Again, since it is a colligative property, so its values will only be dependent on the number of solid particle and independent on the nature. Suppose if you are adding 1 mole of sucrose in 1000 gram of water, okay, then there will be a elevation in boiling point. So this will be your elevated boiling point, which is TB of the solution, and T0B is the boiling point of the pure solvent. Yes, if you have any doubt, then I will make you understand on the board also. But we have to cover larger content. So if you just go on writing, then it will take very much time. Okay. So for that reason, I have to depend upon this slide. Right? Okay. So, and you will get also a very clear picture of getting your notes note down. So in the case of the board, maybe the writing would be fuzzy and it would be difficult for you to understand. So once you are grasping this say presentation thing, then you will be more quicker. Okay. So elevation of boiling point. So TB is the pressure of the solution, and T naught B was the initial. TB is the boiling point of the solution, and T naught B is the boiling point of the solvent, pure solvent. Then the change can be written as TB minus T naught B, which is written as delta TB, and it is found experimentally that this elevation or the increase in boiling point is directly proportional to the molar concentration or the molality. So we can write the change in boiling point is directly proportional to molality. Removing this proportionality sign will introduce a proportionality constant, which is Kb. This Kb is called as the boiling point elevation constant or molar elevation constant or an ebullioscopic constant. And its unit will be what? So just try and derive this unit. It will be the derived unit delta Tb upon m. So Tb has a unit of, so if it is temperature, it will be Kelvin divided by mole per kg. So this can be written as Kelvin kg per mole if you take this thing up of mole per kg. Now remember that this Kb is only dependent upon the solvent. So if you change the solvent, you will change the Kb. If you change the solute, you don't change the Kb. Remember this thing. Further, if we just take the values of the masses as well, then we can write molality as the number of moles of the solute, which is given mass by molar mass, divided by the mass of solvent in kg. So since if your mass is given in gram for the solvent case, divide this thing by 1000 to get it in kg. Just rearrange and get your molality. Then substituting this value of molality in the final equation, we get delta TB is equals to Kb into 1000 into W2 by M2 into W1. Or our main goal was to calculate the molecular mass of solute. So M2 can be written as this equation finally. So remember students, if you want to determine the molecular mass of the solute, you must have the change in boiling point, the Kb value, the weight of the solvent and the solute as well. Here is a question for you. So it is directly from your formula. The vapor pressure of the pure benzene at a certain temperature is 0.850 bar. So this is for the pure thing. Now, after the addition of a non-volatile electrolyte solid whose weight is 0.5 gram, so when it is added to 39 gram of benzene, whose molar mass is 78 gram per mole, the vapor pressure of the solution is now 0.845 bar. So you have to determine that what is the added of the what is the value of molar mass of that added solid substance. So let's see the solution. What are the quantities that we are already aware about? So we are aware about the pressure of the pure solvent. Okay, so it is given here for the pure solvent. Then we are aware about the pressure after the addition of the solute particle, which is this. And the molar mass of benzene is given. The weight of the solute and the solvent both are given. So we know the equation very well for the calculation of delta TB or the molecular mass of the solute. We put all those values. So pressure, initial pressure minus pressure after addition divided by initial pressure. So this is your relative lowering term. It will be equals to the kbm value. Here kb is taken as sorry, kbm not, is equals to the mole fraction. So mole fraction can be calculated as the given mass, which is solute has a given mass of 0.5 divided by the molar mass. It is to be calculated. Then for the solvent thing, we have taken the given mass divided by the molar mass. Again, we have taken the equation, which is W2 by M2, okay, multiplied by M1 by W1. So just we have substituted this thing. From here, you will get your M2 value as 170 gram per mole. Then our next question, it is from the boiling point. So it is given that the boiling point of pure benzene is 353.23 Kelvin. Now, when we add 1.80 grams of a non-volatile solute in the 90 gram of this benzene, the boiling point is raised to 354.11 Kelvin. We have to determine the molar mass of the solute. Again, we have to determine the molar mass. The Kb for benzene is given as 2.53 Kelvin kg per mole. How we'll solve it? For that, we know that the formula for the elevation in boiling point can be written as 354.11 minus 353.23. So this is the amount of elevation. So this is the initial one, and 354.11 is the final one. So final minus initial will give you the elevation. It will be 0.88 Kelvin. Now putting this thing into the formula that we have for the molecular mass in terms of the elevation in boiling point. So it will be 1000 into W2 into Kb by delta Tb into W1. If you have this values, yes, we have this. So for W2 we have this 1.80, W1 we had this 90 gram. Then Kb is given as 2.53 and delta Tb has been calculated here. It is 0.88 Kelvin. Now remember students, don't ever try to convert the change in temperature to a degree Celsius thing, because suppose if you are moving from 0 degree Celsius to 10 degree Celsius, then we can say that we are moving from 273 Kelvin to 283 Kelvin. But for both the cases, for this and this, if you calculate the delta T, then both values will be 10 in the numerical sense. The units may be different, but the value will be same. So 283 minus 273, it is 10. 10 minus 0, it is 10. So if you are given the value of change in temperature in terms of degree Celsius, then you don't have to add 273 to it to convert it into Kelvin. You can directly take it as 10 Kelvin. I hope you are getting my point here. It's very important to understand. Now if you put these values here, you will get M2 as 58 gram per mole. So this is your final answer. Now we have completed two parts of the colligative property. Two colligative properties are still left. So just wait for a while. We will get back with that two properties. The lecture is not over. So we are left with the two colligative property. So 2R will already explained. The next one is the depression in freezing point and osmosis and osmotic pressure, reverse osmosis and water purification, abnormal molar masses, some examples related to it, and lastly in-text questions. So let us continue with our freezing point. Okay. So we have seen that upon addition of the non-volatile solute, there is a decrease in the vapor pressure. As a result of this decrease, there is a lowering of the freezing point as well. So there is an increase in boiling point and there is a decrease in freezing point. So let us try to understand how this thing is happening. If I try to again define the freezing point of a substance, so it is defined as the temperature where the vapor pressure of the liquid phase is equals to the vapor pressure of the solid phase. What was the definition of the boiling point? So it is that temperature at which the vapor pressure of the liquid phase is equals to the atmospheric vapor pressure. But here it is the vapor pressure of the liquid phase is equals to the vapor pressure of the solid phase. Now, whenever these things become equal, then your pure solvent is freezed. So, according to Raoult's law, we know that upon addition of non-volatile solute, there is a decrease in vapor pressure, and as a result, the freezing point also decreases. So, this is the graph for it. Suppose this is your black line. This black line is depicting the vapor pressure of the solid or the solid phase or the frozen solvent. Now, it will increase with the temperature. Clear? And whenever we decrease the temperature, then the vapor pressure decreases. So, this same thing can be said for the solvent as well as the solution. If we keep on decreasing it, we will see that the solvent's vapor pressure becomes equal to the vapor pressure of the frozen solvent at a higher temperature, which is T naught F. Okay, it is T naught F. But for the solution, we get equal condition at a much lower temperature. Again, I am repeating it. So, this black line here is depicting your vapor pressure of the pure frozen solvent. Okay. So, whenever we keep on decreasing the temperature, the vapor pressure will decrease. So, for solution phase, this decrease will cut or intersect the frozen solvent's vapor pressure at a lower temperature, which is TF. So, this is your reason behind decrease in vapor pressure and decrease in vapor pressure and decrease in freezing point. I hope you are getting this thing here. So, if anyone has any problem, they can ask now. It's very important to understand this thing. So, this graph is very important. Okay, so first thing you should always remember that if you are dealing with the thing vapor pressure, then it increases with temperature. Okay, increases with increasing temperature and decreases with decreasing temperature. So, you can say easily that vapor pressure is directly proportional to temperature. So, all of these phenomena can be explained on this basis. So, here I am again repeating it. So, this black line is depicting the vapor pressure of the solid phase or the frozen solvent. Now, of course, this will decrease on decreasing the temperature, but the solvent strikes or intersects this frozen solvent vapor pressure at a lower temperature, at a higher temperature as compared to the solution, and this whole thing is due to decrease in vapor pressure. So, you can see it very clearly from this graph also that the vapor pressure of the solvent is decreased at the same temperature. So, if I just try to make things clear here, then just try to drop a point. So, suppose this is temperature T. Now, at this same temperature, if you see, then you will counter that solution has a vapor pressure here. Okay, but the solvent has a higher vapor pressure at the same temperature, right? So, there we can mark it here. Okay, so we can easily see that at the same temperature, liquid solvent has a higher vapor pressure. And due to this reason only, it is striking the frozen solvent's vapor pressure easily and earlier. Then, if we consider, like our same thing, T naught F as the freezing point of the pure solvent and TF as the freezing point of the non-volatile solute after the addition of the non-volatile solute, then the decrease in freezing point can be written as T naught F minus TF. Now remember students, whenever we write delta TB, it is final boiling point minus initial boiling point. But in case of the freezing point, it is initial minus final because we can't take it negative as TF is less than T naught F. Now, similar to this elevation in boiling point, the depression in freezing point is directly proportional to molality, which is small m. Hence, we can write delta Tf is directly proportional to small m, or removing this sign will give you Kf. This is called as molar depression constant, Kf, molar depression constant or cryoscopic constant or freezing point depression constant. Its unit is again same as the Kb, which is Kelvin kg per mole. If W2 is the mass of the solute and capital M2 is the molar mass of the solute, so we can't take molarity. Okay, so this is, I have when you have seen the slide earlier, then it was written clearly that this derivation is experimentally based. Okay, it is experimental based. So we are getting it directly proportional to molality and not molarity. Okay. So coming on back to this thing. So what do we get? If we put all the values here of molality, we will get molality is equals to weight of the solute, which is given weight by molar weight, divided by the weight of the solvent in kgs. So we have divided this thing by 1000 to convert the gram into kg. Now, substituting the values similar to the case of elevation in boiling point, we get delta Tf is equals to Kf multiplied by W2 by M2 divided by W1 by 1000. Further, just rearranging it will give you this equation. But we are interested in the molar mass of this solute. So we have cross multiplied it to get this equation. And this is your final thing. So I would suggest you just go and try all this calculation by yourself. Then it will be more clear that how we are cross multiplying it and getting the final equation. So this is very important in physical chemistry. Now again, one point is very clear from here, that Kf and Kb are only dependent upon the nature of the solvent and they cannot be estimated for the solute. So you keep on changing the solute. If the solvent is suppose water, and if you are keeping the solvent water constant, then your Kb or Kf value will not change. Okay, so this is very, very important. Now there is a formula to calculate the Kf for the solvent, which is R into M1 into Tf square divided by 1000 into delta H vaporization. Now what are these terms? So R is the gas constant, 8.314 joule per mole per Kelvin. M1 is the molar mass of the solvent. What is Tf? Tf is the freezing point of the solvent and delta H fusion is the enthalpy of fusion. Similarly, for the case of Kb, R is the universal gas constant, Tb is the boiling point of the solvent. So in case of freezing, we have taken the freezing point. Here we are taking the boiling point. Initially, we were taking the enthalpy of fusion. Now we are taking the enthalpy of vaporization. And all of these things should be in Kelvin. Your temperature should be in Kelvin. As I have told you, these are enthalpy of vaporization and enthalpy of fusion. Now coming on to the last colligative property, which is osmosis. So what is osmosis? In osmosis, what do? Is we take two chambers or two compartments. In one compartment, we have this solvent molecule. In the second compartment, we have this solution. Okay. Now we place a semi-permeable membrane in between. Now what do you mean by semi-permeable membrane? You can think it of as a gate which only allows the solvent particle to pass through and not the solute particle. As simple as that. Now this gate can be made up of various type of synthetic and natural things. It can be animals pigment as well and leather as well. So it depends upon the process that we are dealing with. Because solute particles are larger in size, they can't pass this smaller size holes that are present in the SPM or the semi-permeable membrane. So that is the reason the solvent particle can always pass. Now there is a flow from the solvent particle onto the solution side. Means the solvent particle passes through this SPM and goes through the solution part, and this flow is called as the osmosis. If they are of the size, then the process will be neglected. It will be of no sense. Okay. So osmosis is only there if the size is accordingly to control the size of the solute, okay, and not the solvent, or to control the flow of the solute. Now remember students, the solvent will always flow from a lower concentration to higher concentration. So if we are taking two compartments in which one is having the solvent and one is having the solution, of course, in the first case, the concentration of the solute is zero because we don't have any solid particle present, only solvent is there. But in the second case, where the solution is there, we have the solid particle. It means your solvent is moving from a lower concentration to a higher concentration, and this is opposite. So each time you see that the particles move from a higher to lower concentration. Now, why it is happening, I will make you understand with the help of the diagram that we will see later. So here is your diagram, students. So here is your what thistle funnel, which is filled with the solution. Now what will happen? Thus, it is just pumped down in the solvent beaker. The solvent will pass through this semi-permeable membrane. So this is your semi-permeable membrane. This thin line. It will pass from the solvent thing to the solution thing. Now why it is happening? What is the reason behind it? Why is the flow from lower to higher? So if you take the outside concentration, then here your solvent concentration is high. So listen it very carefully. Students get confused here that why is the flow from lower to higher. So outside the thistle funnel, the solvent's concentration is high. But inside the thistle funnel, the solvent concentration is low. Now why it is happening? Why I'm saying this? Because inside the thistle funnel, we have solute as well as solvent. Outside, the solvent concentration can be taken as what? Infinite, because it is the thing that is present. But inside the thistle funnel, we have solute and solvent both. Now, this flow with respect to the concentration, we are moving from a lower to higher. But with respect to the solvent, if we see, then solvent is moving from a higher concentration to a lower concentration. You get my point? So inside the thistle funnel, the concentration of solvent is less as it has the solute also. But outside the thistle funnel, the solvent's concentration is high. So we are moving from where the solvent molecules are moving from a higher to lower. So the nature is following its law. You don't have to worry about it. And why the opposite is not happening? Because the solute particles are not allowed to move through this semi-permeable membrane. As simple as that. So when the equilibrium is attained, the flow is stopped. We will talk about it. Now, many of the phenomena in home occur according to this osmosis, like your shrinking of the mangoes when we keep it in a brine solution. So brine solution means a solution which is filled up of sodium, okay, sodium chloride or the salt. So there is a higher concentration outside. As a result, the water that is present inside that mango will move out. So your skin acts as a semi-permeable membrane, the mango skin. So the solvent or the water that is present inside the mango, it moves out through the solvent, through the SPM and goes into the where? Into the brine solution. As a result of it, if you take out water from it, then it will shrink or it will reduce its size. Clear? Now, this membrane can be anything. Like it can be a network of microscopic holes. You can think it of a network of a submicroscopic holes, which only allows the passage of the solvent molecule and not the bigger molecules like solute. So this type of membrane are termed as semi-permeable membrane. So you must have an idea of what is this semi-permeable membrane. So its definition goes like this, that it is a network of sub-microscopic holes that only allows the movement of the solvent molecules like water and not the bigger molecules like solute, and it can be anything like your pig's bladder or the parchment or synthetic such as cellophane. Now, here is a diagram to how we can stop the osmosis. So if we apply pressure on the left hand side, so this whole flow from the lower concentration to higher concentration is happening due to the pressure. Now if we apply a pressure which is stopping this flow, okay, then that pressure will be called as osmotic pressure. So it is very simple to understand. The pressure that is applied to stop the osmosis is called as the osmotic pressure. So we know that always the solvent molecule which is present here will move to the solution part. And it is happening due to some sort of osmotic pressure. If we apply some extra pressure apart from the atmospheric pressure to stop the passage of the solvent molecule through a semi-permeable membrane, then it has been found that the pressure that is being applied is equals to the concentration of the solution multiplied by R into T. So this equation is very simple to understand. It is concentration in terms of molarity. So here we take molarity. So this pressure is applied onto a higher concentration side. Okay, so because remember, suppose something is pushing from the right to the left, okay, and you want to stop this pushing, so you will apply opposite pressure. So of course you will apply on this side. Okay, so suppose water is flowing from your pipe and there is a motor. If you apply pressure from the motor side, the flow will be more rapid, right? So you have to apply pressure on the opposite side to stop that flow. As simple as that. Okay, so just try to understand the simple analogy. I hope you are getting my point here. So our flow is from right to left. So you have to stop it, right? So we'll apply it on the opposite side. Okay. Now, putting the values of concentration in terms of molarity, it is number of moles of solute by volume of the solution in liter, which is the definition of molarity. Now, if we keep on substituting the values similar to our previous colligative property, you will get pi into V is equals to W2 into RT by M2. You can just try this sum by yourself. It's very easy to understand by substituting N2 values. You will get M2 is equals to W2 into RT by pi. Now, this osmotic pressure has a advantage over other methods in calculation of the molar mass of the solute because it is dependent upon the molarity and not upon the molality. If you have studied molarity and molality difference very minutely, then you must know that molarity is much more better than molality. Okay, because molarity is dependent upon volume and volume is a function of temperature. So it gives you a specific volume which is of the temperature dependence. So if you are studying a scientific thing, then you must specify the temperature. In case of molality, the two different concentration may give the same molality as it is dependent upon mass. But this is not true for molarity and hence it is more scientific in nature. Now this technique is very useful for many other things. Okay. So what does it mean? Volume greater than mass. Can you ask it more clearly? So suppose if two solutions have the same osmotic pressure, there were two chambers in the previous slides you have seen. Now if you keep the two solutions which are having the same osmotic pressure, then in that case, there will be no net flow. For example, if you take two compartments, in the first, you are filling the blood which is equivalent to that of the 0.9% sodium chloride solution. So in one side you keep the blood cells, on the other side you keep the 0.9% sodium chloride solution. Then you will see that there is a no net flow because both have the same osmotic pressure. Okay, but if it is more than 0.9%, then the water will flow into the blood cells. Suppose you take a blood cell. So blood cell will also have some concentration and you keep it in a salt solution. Okay. Then if this salt solution has a greater osmotic pressure, then what will happen? the solvent will move into the blood vessel, or your blood cell will be filled of water. And if the case is opposite, okay, if the case is opposite, then water will flow outside the cell. Such a solution is called as hypertonic. So it is written here that if the salt concentration is less than 0.9%, then the solution is said to be hypotonic, and if it is less, it is called hypertonic. In this case, water will flow into the cell. So if anyone has any question, they can ask. So is volume greater than mass? So it will be dependent upon the say thing which you are dealing with. It is possible that the liquid phase can have a greater mass and a smaller volume. It is possible that the solvent can have a smaller volume and a greater mass. It is not fixed. Okay. So these 2 points are very, very important. Now here are some more examples. The first one is of raw mango. Second one is of the flower. So you can just go through these points or the applications once again. Then we have the carrot example. So they all are similar to this. So you can think the same thing of the people who are taking more salty food. They would see that there is retention in the water retention in the tissue cells because of the same hypertonic and hypotonic thing, and it is called as edema. Similar to that, the water movement from the soil into the plant roots are as a result of osmosis. Similarly, the meat is preserved by keeping it into a salty solution. You can just get through each of these points so that you can get a clear picture of what is osmosis and how it is helping it in nature. Now, this flow of solvent molecule can be reversed. So in the first case, we have seen that if we apply the pressure that is equal to the osmotic pressure, then the flow will stop. But if you apply a greater pressure than the osmotic pressure, then the flow will be reversed. This process is called as reverse osmosis. And it is used in distillation of seawater. Here is a diagram for you. Suppose we have fresh water here. So only the solvent molecule is present here, right? And here we have the salt water. Initially, what would happen if we don't apply any pressure? The fresh water will move on to the salt water. This is normal osmosis. But if you keep on applying the pressure, finally, the solvent molecule from the salt water will move to the fresh water. And the volume of fresh water will increase. As a result, you are purifying the salt water. So this method is used in the case of distillation. So you are asking that what will happen if we keep? Yes, the same thing will happen. Okay. Now, as a result of this, the pure water is squeezed out of the seawater and we get a pure solution. Now, reverse osmosis can only occur when we apply a pressure which is larger than the osmotic pressure. Then only we will see the reverse osmosis. So if you apply a pressure greater than pi. So a very well working SPM or the semi-permeable membrane is cellulose acetate. So it is used in the purification of water. Here is a question for you. So we are adding 45 gram of ethylene glycol in 600 gram of water. You have to calculate the freezing point depression and the freezing point of the solution. How we'll do it? So the molality of the glycol can be calculated as the moles of the ethylene glycol by mass of the water in kilograms. So we have to move it from the right side to the left side. So we apply pressure on the higher concentration. Okay. We apply pressure on the higher concentration. similar to the previous one. So we were applying in the solution higher concentration. In this case also we'll do the same thing. Now it will be how first we need the moles of ethyl glycol. So given mass by molar mass, it will give you 0.73. Mass of water will be 600 by the 1000, which will be 0.6 kg. Now molality can be calculated as 0.73 by 0.60, which is 1.2. Just put these values. And therefore, freezing point depression can be calculated as delta TF is equals to KFM. So KF value will be given in your question. You don't have to worry. So this question is from the NCERT, so it is not given because the textbook itself has this value. But in the case of your examination questions, this will be given. Multiplied by the molality will give you 2.2 Kelvin as the depression. So this is your final freezing point. So how you will calculate the final freezing point? We know that delta TF is equals to the elevated freezing point, the pure solvent freezing point minus the solution freezing point. So delta TF is 2.2. For pure solvent, it is 273.15. Why I am taking it? Because the water is solvent. Okay, and water has a what? It has a freezing point as 0 Kelvin minus TF. So TF will be finally equals to 273.15 minus 2.2, which will give you 270.95 Kelvin. Now we will move to abnormal molar mass. So what happens? We know that the colligative property is dependent upon the number of solid particle. We know it very well. So whenever we are increasing the number of particle, we will increase. Yes, we will do it. Just wait for 2 minutes. I will explain this whole thing in the next class. If you want to go, you can leave. So I'm just giving a small introduction right now. We will come back to with this topic once again. Okay. I'm just giving a small introduction. So what will happen when you are dealing with the ionic thing? Then suppose we are assuming that okay, we are dissolving one KCl molecule. But actually what will happen? When it will go to the solution, it will dissociate as two particles. So basically you are getting two particles out of one. And we know it very well that colligative property are totally dependent upon the number of particles. As we are increasing the number of particles by dissolving it in the solution phase, therefore the colligative property will change. Now, if we ignore the interionic interaction, then we will see that the boiling point is being doubled here. Okay, so if we just try to calculate, then we will get a double boiling point, which is very wrong. And why it is happening? Because of the two particles. So remember students that due to this increasing the number of solid particle, the molar mass is always lower than the true value. Similarly, in the case of benzene, there is an association due to hydrogen bonding, and as a result, there is a decrease in number of particles due to this dimerization, and hence this equation can be written for this dimerization, and this is your dimerized molecule. Now, due to this dimerization, the delta TF or delta TB is being halved. So in case of dissociation, the elevation is doubled or the depression is doubled, but in case of association, it is being halved. And we get a molar mass which is not equal to the normal molar mass of the solute that we know. And this thing is termed as abnormal molar mass. So this was all for today's lecture. We will try to understand it in a much better way with more examples. Till now, just wait for a while. We will get back with this thing. So dimerization is association of two molecules. Okay. So in few minutes, our next faculty will join you. Thank you for joining the session. So we'll cover 2 chapters. Okay. So for a Hindi lecture, you can just go and visit our website for the same.